Now that we've introduced vectors, we're going to study their attributes a bit more carefully. In the case of geometric vectors in R2 or R3, for example, we've already established that they are entirely characterized by their length and direction. But what about length in particular? How do you measure it? Do you have to use a ruler? Like get out a ruler and actually measure the length of the vector between 2 points? Well, what if you don't have a good drawing of the vector? What if the only thing you have is a rough sketch and it's not to scale, so measuring it would be useless? Okay, we're going to solve this problem by providing a definition for length of a vector that relies solely upon its coordinates. And the good news is it's not just going to apply to geometric vectors in R2 or R3, but it'll also apply to general coordinate vectors in any dimension. And that's what this section is about. So this is called norm, dot product, and distance in Rn. So we're going to start with the idea of norm, which really is just another word for length of a vector. So here's the definition. Let's say you've got a vector x, and this definition, like I said, is going to work for any vector in any dimension. So we're going to just say let it be written in as a coordinate vector in Rn, where n could be absolutely any positive counting number. So we've got the coordinates x1, x2, all the way up to xn, its last coordinate. Okay, so we're going to define all of these three words mean the same thing: the norm, the length, or the magnitude of the vector x is defined as follows. So first of all, the notation that you use is you just write down the vector x and you use double bars on either side. It's kind of like the absolute value notation, but you just use double bars on either side instead of single bars. Okay, and well, how do you calculate it? What you're going to do is you're going to take each of these coordinates. Each one of these coordinates is going to play a role in the length of the vector x. What you're going to do is you're going to square each of them, and then you're going to add them up, and then take the square root of the result. So if you write that out carefully, you'll get x1 squared. That's the square of the first coordinate. Then you're going to add the square of the second coordinate all the way up to the very last coordinate. So you're going to square each of them, add them all up, and then once you do that, you'll take the square root of the result. So this is our definition for the length of a vector. Or my favorite word is norm. That's why I put it first in the list. You'll hear me use the word norm quite often, but just think length. So all three of those words mean the same thing: norm, length, and magnitude. Okay, and I've mentioned it below as just a passing remark. In R2, if in the specific case where x happens to be a two-dimensional vector, well then you'd only have two coordinates. And if that's the case, your sum would actually stop here, and you would only have that expression for your length, which really is nothing but the Pythagorean theorem, which I'm going to just show you now by drawing a picture. And this is a helpful picture to kind of help wrap your head around why this formula is written down the way it is. I call it a formula. Really, it's a definition, but there's nothing wrong with calling it a formula. Definitions can also be formulas. Here's the picture of what's going on. Let's say we had a vector in R2. So let's draw the Cartesian plane here. And I'm going to draw the vector in a specific way so that its initial point is at the origin. So this is going to be its initial point. And let's say it's got some terminal point out here, given by x1 and x2. So if I write it as a geometric vector from the origin to that point, it can also be expressed as a coordinate vector with those two coordinates. Okay, so let's say that's our vector x, which I'll label it on the picture. All right, well, what does the definition of length say? Well, forget about that for a moment. Let's just look at this picture closely. Pretend you didn't have this formula available. Pretend you didn't have this yet, and we were just looking at this picture, and you were trying to measure the length of this vector, and all you had, but by the way, what I mean by that, the length of this vector, is just the distance between these 2 points. Well, one way to approach that might be to do the following. You'll look, okay, those two coordinates are the coordinates of this point, but what if we just drew it as a triangle? Just kind of added that vertical line. Right, I've drawn it hyphenated. Just go from that point and go straight down to the x-axis, and it's going to hit the x-axis right at the point x1. And you know that because x1 is the x-coordinate of this point. Okay, so, well, what good is that? Well, what's the y-coordinate of this point? It's x2. That means right over here, you can draw an x2. And the point is you now have access to the side lengths of these of the triangle, right? You've got the length of this side, it's going to be x1. So if I measure this, it's really just x1. And if I measure this side over here, it's actually going to be x2. Well, what does the Pythagorean theorem say? Do you remember that? Or sometimes people just nickname it as Pythagoras, which is the name of the author of this theorem. Really, it just tells you the following, right? If you have a right triangle, in general, I'm just drawing a general triangle here, that it happens to be a right triangle, and if I label the sides A, B, and C, well, the Pythagorean theorem just tells you that the square of the length of the hypotenuse, which is really just c squared, is equal to the sum of the squares of the other two sides, which would just be a squared plus b squared. So it just tells you that a squared plus b squared is equal to c squared. So if you applied that over here, well, what would your c be? Your c would be the length of this vector here, the length of the vector x. So in other words, you'd have, well, let's do the left-hand side first. The sum of the squares of the two smaller sides, so you'd have x1 squared plus x2 squared. So you'd have x1 squared plus x2 squared is equal to the length of the hypotenuse squared, which would just be the length of the vector x squared. So if you solved for the norm of x, you'd just be taking the square root of both sides. And if I write it with the norm of x on the left-hand side, what I would just get is this. I'd get the norm of x is equal to the square root of x1 squared plus x2 squared. Which really, that's exactly what this formula would give you in the case where your vector was a two-dimensional vector, right? If you were in R2, then these would be the only two terms you have underneath the square root. So, but if you are in R2, then you can draw the picture, and you can derive the formula this way. But this is just a specific case of this more general formula. So this works in general, but this is the justification for why it works in R2. Okay, let's look at some examples. The good news is, because we have this formula, we don't have to draw the picture every time, right? So you can just go ahead and use the formula. So let's say I had the vector x given as a vector in R3. So it's got three coordinates, -3, 2, and 1. Let's say that it's a vector in R3, and let's calculate its norm. So the length of the vector x, well, we're just going to take the square root, and I'll just leave it partially drawn so I can fill in the terms, and then we can finish that symbol after. Let's take the square of each of those coordinates and add them up. So we're going to take the square of -3 plus the square of 2 plus the square of 1. Right, and what are you really going to get here? -3 squared is 9. 2 squared is 4. And then 1 squared is just 1. Right, so you've got 9 plus 4, 9 plus 4 plus 1. That just adds up to 14. So really what you have is the square root of 14. Now, can you go any further than that? Can you reduce it? What is the square root of 14? Don't even worry about grabbing, don't even reach for the calculator. This is an irrational number, right? 14 is the product of 2 and 7, and 2 and 7 are both prime numbers, so you're not going to be able to reduce this at all, and it's not advantageous to plug it into your calculator at this point, unless you're just curious. Go ahead. But formally, this is the length of the vector, because we want to stay exact. Let's do an example of a vector that's in a higher dimension. So let's say a 4-dimensional vector. How about we get the vector y, which is going to be given in terms of its coordinates like this. We've got 2, -1, 3, and -5. So that's a vector in R4. And what's its length going to be? Well, use the same strategy. You want to calculate its length, just add up the squares of each of the coordinates, and then take the square root of the result. So we have, well, the first coordinate is 2, so you have 2 squared plus -1 squared plus 3 squared plus -5 squared. Right, so if you actually add all those up, -5 squared, that's positive 25, 3 squared is 9, this will be 1, and that'll be 4. Right, and if you add them all up carefully, what you end up getting is 39. So this works out to the square root of 39. And again, you can't reduce it. 39 is equal to 3 times 13, actually. So, and 13 is a prime number, and so is 3, so you're not going to be able to reduce that at all either. So that's a good place to stop. And that's really all there is to computing norms using the formula. If you have access to the coordinates, it's straightforward. Just plug them into this formula. This will get you the length of any vector. Okay, so now that we've got a new definition, it's going to come with some properties. Right, so let's take a look at a few things you can say about norms of vectors. So that's what this theorem is going to consist of. So let's say we've got some vector x, and I'm not going to write out its coordinates this time because we're not going to need them. We're not going to refer to the coordinates in any way. All we need is a vector x, and it can be any dimensional vector, so it could be a 5-dimensional, 10-dimensional, 100-dimensional, doesn't matter. Any coordinate vector at all. And then k will just be some scalar, because we'll need it for one of our properties. Okay, so the first statement of this theorem just tells you that the norm of the vector x is always going to be greater than or equal to 0. Okay, and the second statement is related to the first statement. Well, notice that I said greater than or equal to 0. Right, so that doesn't rule out the possibility that the norm of this vector x could actually be 0. But the second statement is going to tell you exactly when that can happen. It's going to tell you that the only way that can happen, so, and I'll write it out as I say it, so that the norm of x is equal to 0. The only way that this could actually happen, in other words, if and only if, the only way that can actually happen if x itself is the 0 vector. So that's how we'll write that. Okay, so that's the second statement. So for any other vector, if your vector is non-zero and you calculate its norm, you're going to get a positive number. But if you calculate the norm of the 0 vector, you're going to get 0 exactly. That's the combination. That's really what the first two statements combined tell you. Now the third statement, in language, the way we like to articulate this sometimes, and you don't need to be concerned with it, but if anyone's interested, the phrase that we'll use to describe the third property of norms is that we say that the norm of vectors in Euclidean space, the norm is a positively homogeneous function. But what that means mathematically is a little bit easier to write down. So let's just say the following. If I want to take the norm of the scalar product k times x, right? So remember, k was a scalar. I can multiply it onto the vector x, and then I take the norm of the result, right? Because if I take a vector x and I multiply it by a scalar, the result is still a vector. So this makes sense to write down this notation. But what this is going to give me, it turns out, and you might ask the question, can you pull the scalar k out of the norm, out of the length function? And the answer is yes, but it's going to cost you an absolute value sign, right? So what this will be is it'll just be the absolute value of k multiplied by the magnitude of the vector x, or the norm of x. So notice I didn't write the norm symbol around k. I just wrote the typical traditional absolute value notation, because k is not a vector. K is a scalar. Right, so that makes sense. It would, if I wrote the norm notation around k, that wouldn't actually make sense because k is not a vector. Okay, so that's our first theorem about the norm formula, and we're going to prove this on the next page.